Okay, it's 2 o'clock. Let's go ahead and start. So I apologize for last lecture we had. I'm really not sure what happened there. The picture just kind of didn't work, but hopefully it won't happen this time. So we're going to go back over what we did last lecture with logs. So what we said last time was we know how to solve all sorts of things, but what if we have something like 2 to the x equals 30? Well, we don't really know what to do there, do we? We have an x, and we know we need to get it by itself. We need to solve for it. But how do we get that x out of the exponent place? Because how would you isolate that exponent? Well, the way we do that is with logs. So the first thing that's important here is to know how to go from what we call exponential form to radical form. So exponential form is going to be something that looks like b to the x equals y. Okay? So we have 2 for our b, x is obviously x, and then 30 for our y. Now b is the type of counting system that we're using. So for instance, we're using 2 here. What I mean by that is if we think about the powers of 2, so 2 to the first is 2, 2 to the second is 4, 2 to the third is 8, so on and so forth. That's the counting system. We're counting by the powers of 2. So the b is called the base, and the base is defining what our counting system is. Now to go from exponential form to logarithmic form, we need to switch a few things around. First of all, we need to define a log that we're going to use. The log that we're going to use is going to be defined by the base, the b. Okay? So what counting system are we talking about? What number are we raising to a power? What base do we have, in other words? What is our b? So in this case, we have 2 for our b, so that's going to be log base 2. And then we are going to take the log of 30. We're taking the log of that y. So what this says so far is if we are counting in powers of 2, how far do we have to go until we get to 30? That's what a log says. Again, if we're counting in powers of this number, how far do we have to go till we get to this number? So in this case, we'll have to go X amount of distance. We'll have to go X amount of steps in that power. Okay? So again, this is converting between exponential form and what we call logarithmic form. Now this is useful to us because we can convert this thing into something more like this, and this is actually something that makes sense to us if we want to go further with some math. So instead of using this sort of form, we know now what x is. It's log base 2 of 30. which we could plug that into a calculator if we wanted to get the exact, or if we wanted to get an approximate number, not the exact. However, if we wanted to continue plugging x into something, this is going to be more useful because it's the exact form. Okay? Now, how do we get here? How do we go from exponential to log? How do we know that this works? Well, it's by using some rules, some properties of logs. Okay? So before we go any further, let's go ahead and go over the properties of logs. Like I said with the previous lecture, these properties of logs come from our power rules. So remember that we have rules for when we're dealing with exponents. So for instance, if I have x squared times x to the third, well, what we would do there is we would we would add the exponents. So x squared times x to the third, we add 2 plus 3, and we get the total there is x to the fifth. And then we also have some rules for when we're dividing things with exponents, when we're raising an exponent to another power, so on and so forth. And that's where these new rules that I'm going to introduce you to come from. So for instance, that first one that I just said, the product rule. Logs also have a product rule. So the product rule says that if we have log base b, whatever, of two numbers that are multiplying, so let's say x and y, x times y, then what this means is that we can rewrite this as, instead of multiplying x and y, we will have two logs, log base b of x plus log base b of y. Which again, like I said, our product rule for powers, it says that if we have two numbers that we're multiplying, we're going to add their powers. Well, here we have two numbers that are multiplying, we're going to add. Same rule. It's just now it's in terms of logs. So we can expect sort of the same things that we saw with powers to happen with logs, which, yeah, let's go on to quotient rule. So let's see, when we were talking about powers, the quotient rule said that if we have two numbers that we're dividing and they have powers on them, then we will subtract those powers. Same thing with logs. If we have the log base b of x divided by y, so again, two things that are dividing, we can rewrite this as log base b of x minus log base b of y. Again, it's exactly like our power rules. Okay, next one. If we take a power of a power, so exponent raised to another power, then we multiply those powers, right? Well, same thing here. If we have log base b of x to the y, then what we can do is we can rewrite this as y times log base b of x. Okay. So remember, if you have any questions, you can just go ahead and type them into the chat, and I will get to them as soon as I see them. Now, these are not all the rules, but they're the ones that we need so far to get from here to here. Again, why is it that we can just go from this to this? Let's see. Again, 2 to the x equals 30. Something that we can do just on the fly, anytime we really want to, is we can take the log of both sides. So if we have an equation, particularly like this one, where we have x in a power slot like that, we want to get x out of that slot. So we can do the log of both sides. Now we have to define what our base is anytime that we do that. With an example like this, probably a good idea to use the base 2. Okay, so log base 2 of 2x, or sorry, 2 to the x, equals log base 2 of 30. Again, all I've done here is I've taken the log of both sides. That's it. And again, you can do that anytime that you want. You can use any base that you want as well. I didn't have to use base 2. I could have used base 10. I could have used base 50. It doesn't really matter. It's smart to use base 2 here, though, to match this 2, and I'll show you why in a moment here. Okay. So if we look at our power rule says that if we have something raised to a power inside of our log, like we do here, 2 to the x, raised to the y. So what we can do is we can take that power and stick it out in front, so we just have this log by itself. So we'll go ahead and do that. So take this x, throw it out in front. X times the log base 2 of 2 equals log base 2 of 30. Okay. So now, let's see. What is this telling us? It's in logarithmic form right now. Let's think. If we put that back into exponential form, that would mean that 2 to some power gets us this. Remember, what logs are asking is how far do we have to go in this thing's powers to get to here? So what power of 2 gives us 2 is what this is asking. Again, what power of this number gets us this number? Well, 2 to the first power gives us 2. So, log base 2 of 2 is 1. Meaning that this is really x times 1. Well, x times 1 is just x, isn't it? We don't need that 1. So x equals log base 2 of 30. And again, that's how we go from exponential form to log form. But, do we need to do that? Nah. Since we know the general form, we can just go from here to here. We don't need to do all that math. But it's nice to know why that works. More importantly, we have a new idea here with this log base 2 of 2. So here's another rule for us. Base rule. Basically, if our base matches the number that we're taking the log of, it'll always be 1. So if we have log base b of b this will always equal 1. Which is nice because, I mean, multiplying by 1 doesn't really change anything. Essentially, this will help you cancel things out. That's why I chose to use base 2 here, because I knew that if I had base 2 here with this 2 next to it, if we're taking a log of 2 and we have a base 2, then it's going to cancel. Okay. Another way to think about this. So another way to think about the base rule is that if we have log base b of x to the y, so this is also the power rule that we're really thinking about here. If this x is really matching b, then we know that these two will cancel, leaving us with this, which should be out here. Well, if we have that, then this just equals y. So essentially what we're saying here is if we combine the power rule and the base rule, in the case where the log base b and the thing we're taking the log of, if the b and the thing we're taking the log of match, then we just have that power of whatever that thing is. Is this really important to know? Not really. You could probably figure it out as long as you know the power rule and the base rule. But this is just a nifty little thing if you want to use that shortcut. Some other interesting things to know. If we have b to the log base b of x, that will also cancel and just give us x. If we have log base b of 1, this will always give us 0. Because if we think about it, what we're asking here is, what power do we raise b to get to 1? Well, anything to the 0 power is 1, so 0 power. Okay. So the rules that I want you to remember, the rules that I want you to write down right now and have stored somewhere so that you can recall them, are the quotient rule, the product rule, the power rule, and the base rule. These 4 right here are going to be very important as we keep going on through logs. So I'll give y'all a moment to copy these down. Okay. If you haven't quite got them all down yet, of course, you can come back and look at the recorded version of this lecture and get them that way. But let's go ahead and move on. Let's put some of this into practice. Okay, so very similar to what we were just looking at with 2 to the x equals 30, let's try 4 to the x equals 27. Okay. So what we did last time when we wanted to evaluate this was we took a log of both sides, and then we moved x to the front and did all that stuff, but we know that it basically just came out to be converted to logarithmic form, right? So let's go ahead and convert this to logarithmic form. So our logarithmic form, first of all, we need a log, and we need to know what base we need to use. Well, of course, the base is the thing that we're raising to powers. It's the counting system that we're using. So what are we raising to a power here? We're raising 4. So log base 4. And then what are we taking the log of? Well, again, logs ask, we're raising this to a power, and then that gets us some number. So how many times do we need to raise this to get this number? Well, the number that we're getting is 27, so that's what we're taking the log of. And we know that equals x. So once more, what we have here is the exact form for x. Exact form because all of the information for x is contained in there. This is different from approximate form, an approximate answer. We could plug this into a calculator and get an approximate answer. And what I mean by that is that we could plug it in, but we would have to round the answer. We wouldn't get, just a nice, neat little number. It's just going to be something weird, something with a long decimal that's going to keep going on and on and on forever but never repeat. So again, we'd have to round it. That's why we prefer this when we're doing math, because all of the information for x is in here, and we can keep doing calculations with this number, and we're not going to lose any information from rounding. However, if we wanted to put this into the calculator and get some number, some approximation, it's not as easy as just plugging in some numbers. Calculators, even this one, don't have every single base out there. Okay, so they don't have base 4 typically. Instead, they'll be programmed with something like base 10, usually base 10. So how do we plug this into our calculator if it doesn't have base 4 logs, if it only has base 10 logs? Well, for this, we use what's called the change of base formula. So the change of base formula goes like this. If we have log base b of x, so something like this, we can make it into log base whatever we want. We'll say a of x over log base, again, a of this time b. Okay? So we can use this to put into the calculator, and this changes the base. Again, this a can be whatever we want. Of course, it has to be the same a on the top and the bottom. But this allows us to calculate it with a calculator. So I've got my calculator right here. I've got log base 4 of 27, so I want to put that into this form. Okay. So what I need to do is put into the change of base formula. So log base, let's see, my calculator has base 10, so I'm going to use base 10. Log base 10 of x, so 27, over log base 10 again of this time whatever my original base was, which in this case is 4. And that'll give me the answer for this. So let's see that. Let's do log of 27 divided by log of 4. And we get an answer of about, not sure how easy that is to see on the screen, but of about 2.377443751, so on and so forth. Of course, we need to round that. And I'm going to say that this is 2.37744. Again, about. Okay. So again, this would be what we want to use if we want to continue doing calculations, if we want to continue manipulating this and solving things. But once we get down to the end and we want a number that we can use maybe in the real world, this is what we would want. Okay, let's take a look at another one. How about 9 to the x equals 3? Well, how can we raise something to a power and then get something smaller? It doesn't seem to make sense, does it? Okay, so in this case, I'm not going to do the whole change from exponential form to logarithmic and whatnot like that. I want to try to solve this a different way. I want to take the log of both sides first of all, because something weird is going on here, isn't it? Okay, so I'll take the log of both sides. Okay, and I need to decide a base. Well, I'm going to use base 3 for 2 reasons. First of all, I know that if I put base 3 over here, that log base 3 of 3 is 1. So that's something that I know. I can actually get a value out of that. The other reason I want to use base 3 is because if I put base 3 over here, I know that there are 3's in 9. 9 is 3 times 3. I know that. So maybe that'll help us in a minute here. But let's move on. Let's keep doing some steps. Okay. The next thing that I see is that we have 9 to the x. Now, using our power rule, we know that the x can go out in front. So now we have x times log base 3 of 9 equals log base 3 of 3. Okay. Now the next step takes a little bit of kind of practice. Again, what I said before is that 9 is 3 times 3. That's why I used base 3 here. Well, 3 times 3, that's 3 squared. So I can rewrite this as 3 squared. And that will do something else for me. I've got my power rule happening again. Again, if I have a power here, then what I can do is I can take it and put it out in front. So now, let's see, x times 2, that's 2x, times the log base 3 of 3. Okay, well now I have log base 3 of 3 here. I know that's 1. Again, log base 3 of 3, that's 1. So really what I have here is 2x times 1, that's just 2x. And again, log base 3 of 3 is 1. So I have 2x equals 1. This is definitely something that I can solve. Just divide by 2 on both sides. And I get that x equals 1/2. Now this should be familiar. This should be sending off something in your head right now. What we just found is that our power, what we need to raise 9 to in order to get 3, is 1/2. So we have 9 to the 1/2 power equals 3. Again, this should be setting off something in your head. 9 to the 1/2 power, particularly the fact that we're raising it to a fraction power. Remember that fraction powers represent roots. So this is from a long time ago, I know. What, 2-3 months ago? And so again, rational exponents, fractions for powers, represent roots, represent radicals. The denominator of that radical, the denominator of that fraction is going to be the number that goes in crook here. So we have a square root. We're taking the square root of 9, and the numerator, the number up here, is the power we're raising 9 to. Well, 9 to the first power is 1. 9 to the first power is 9. And the square root of 9 is 3. So that makes sense. Now, again, with some practice, you could probably just look at this and say, oh, well, it's 9 to the 1/2 power. Or maybe we have something like 8 to the x power equals 2. Well, I know 2 to the third is 8, but we're going the opposite direction, so this has to be x equals 1/3. In other words, the cube root of 8 is 2. Okay. So once again, if you have questions, please put them into the comments in the chat. Okay. Let's try something different. So you might encounter something like this. Log base 2 of 7x to the third over y. Well, this seems pretty complicated. There's a lot of stuff going on inside of this log. And, well, because there's so much stuff going on in there, it's kind of hard to work with this type of log. Now, if we remember back to our properties of logs, the rules that we were going over at the beginning of lecture today. In fact, let me get those again. I wrote the arrow as a double-sided arrow. That's because we can go from here to here or from here to here. We can expand it or we can condense it. And that's actually going to be something that we want to do here. There's just so much going on inside of this log that it probably would be better to split it up as separate logs so we can look at each of those individually. So let's go ahead and expand this one out, see what it looks like. Okay, so once again, looking at our rules here, well, I see that the thing we're taking a log of is a fraction, and that immediately makes me think of the quotient rule. So the quotient rule says that if we have something like this, that we're taking a log of a fraction, we can split it up as two logs that are subtracting. So let's go ahead and do that. So I'll have two logs now instead of just one, both of them log base 2. The first one will be the top part, 7x to the third. Then we're going to subtract another log, log base 2 of the bottom part, y. Okay. Well, that's nice. This looks pretty good. That's pretty simple. But this one still has stuff going on inside of it. So let's look at our rules again. I see product rule. So I've got 7 times x to the third. And the product rule says that if I have log of something times something, again, I can split those up as two different logs that are adding. So, again, I'll split this up into two separate logs. Log base 2 of 7 plus log base 2 of x to the third. And then, of course, I still have minus log base 2 of y. Okay. Is there anything else I can do to make this bigger? Well, let's see. Log base 2 of 7, that's pretty simple. Again, we said that log base 2 of y is pretty simple. Log base 2 of 3 to the x. There's another rule that we can use. Power rule. Power rule says that if we have the log of something raised to a power, we can take that power and multiply it by the log. Okay, so take this power, throw it out in front. We now have log base 2 of 7 plus, let's see, we threw that 3 out in front, so we now have 3 times log base 2 of x minus log base 2 of y. Okay. So this is about as far as we can expand this one out. But if we had, let's say, equal signs, so this equals something, instead of trying to get this thing and solve with this kind of balled up mass of different operations, we can separate these out as these different logs, and now we have things that are much simpler to work with. For instance, I could just subtract log base 2 of 7 from this side and bring it to the other side, and then I'd have x and y. It's just a matter of which one do I want to solve. Do I want to solve x or do I want to solve y? But again, expanding this out can mean the difference between something super complicated that probably not going to be able to work with very well, or several things that are much simpler. Of course, we can also go the other way around. Let me get one of those. Yeah, that works. Let's say we have log base 2 of 3 minus 5 times the log base 2 of x minus 2 times log base 2 of 4. Really? Log base 2 of 4? That's a really interesting example. I just pulled it off from Google. Okay, so again, we can go the other way around. Instead of expanding these things out, we can condense them. So what else can we do here? I see powers. We've got these things that are multiplying by our logs. Those really represent powers. So log base 2 of 3 minus, this 5 is going to become a power of x. So log base 2 of x to the 5th minus, again, this 2 is going to become a power of 4. Log base 2 of 4 to the 2nd. Okay. Then let's see. Oh, I'm sorry. I've got this wrong. This is supposed to be plus. All right, then we can use our product rule. We said we have a log plus a log. That really means we can multiply 3 and x to the 5th. So log base 2 of 3x to the 5th minus log base 2 of 4 to the 2nd. And then we have minus here, so we can use our quotient rule and make this log base 2 of 3x to the 5th over 4 to the 2nd, which I'm going to go ahead and say is 16. Okay. So that will just about do it for today. Now, remember, Wednesday is the start of our Thanksgiving break. Then, after we come back from Thanksgiving break, we have Monday and Wednesday. Then we have class, but no other class after that. So that means that we have 2 class periods left. Well, I really don't have anything else to teach y'all. What I want y'all to do instead, and I've said this before, is those days, and hopefully not just those days, but some more time than that, use that time to work on Hawks and get as much done as you can on Hawks. I want everybody to hopefully get done with everything on Hawks and be well prepared for the exam. Again, Monday I'll be making a review and sending it out, Monday the 30th, sorry. Monday the 30th I'll be making a review and sending it out for our exam. That exam will be Friday. I'm just going to send out the exams to everybody, all of my classes on Friday, so you have plenty of time to work on them. They will be due, of course, the Thursday the 10th. Okay? And I will not accept anything after Thursday the 10th. If you, for some reason, don't have the ability to turn it in before Thursday the 10th, you need to tell me right now today, okay? So I will not be accepting any work after Thursday the 10th, especially not exams. All right. But again, I think that does it for today. I hope y'all have a good holiday. I don't know if you're going back to see your families or not. The coronavirus is, of course, pretty crazy for everybody right now. Oh, but remember, if you do go back to wherever town you're from and you leave campus, you are not allowed to come back to campus. You can, of course, stay online, but if you do leave town and go somewhere else for the holiday, you're not allowed to come back to campus. At least that's what the president has said. Okay, so I will see y'all later. I hope you had a great semester, and I hope you have a great holiday, and continue to have a great year.